Hello students, welcome to the EPG Pathshala. I am Ashok Goyal from the Department of Physics and Astrophysics, University of Delhi. In this module, we will discuss the boundary value problems. Remember that boundary value problems occur all the time in physics applications. So, we will discuss this problem in somewhat detail from the paper Mathematical Physics. So, let us see what we are going to learn in this module. In this module, we will learn about the nature of eigenvalues and eigenfunctions of a Hermitian differential equation in relation to the boundary values imposed on it. Given the differential equation, the complete solution involves specifying the value of the unknown functions or its derivatives at points within the domain of the equation. The number of such specifications depend upon the order of the differential equation. The most commonly encountered equations in physics are of second order equations for which we require two specifications, which means that two specifications need to be made for the complete solution of the equation. Consider the equation d2y by dx square plus p of x dy by dx plus q of x y is equal to gx as the second order ordinary differential equation to solved in the domain x lying between a to b, where the functions px and qx are real, continuous in x, for x in this interval, and the solution should satisfy certain boundary conditions which are commonly of the following type. The boundary conditions under which we have to solve the differential equation have to be specified and are commonly of the following type. Number 1, Dirichlet type. This type of boundary condition specifies the value of the unknown function at the endpoints of the interval. That is, at the endpoints of the interval, you specify only the value of the function, not its derivatives. Then another type of boundary condition, we have the Nyman type. In the Nyman type of boundary condition, the derivative of yx at the end points is given. For example, dy by dx at x equal to a is specified as, let us say, ya prime, and dy by dx at the endpoint b is specified as yb prime. That is, in the Dirichlet type of boundary conditions, it is the value of the function that is specified at the ends of the boundary. In the Nyman type, it is the derivative of the function that is specified at the boundary. Now, there may be boundary conditions where both the function and its derivatives values at the boundaries are specified. This is mixed type of boundary condition, and this is a combination of the Dirichlet and Nyman type and specifies certain combination of the function yx and its derivatives at the endpoints. For example, alpha times the value of the function at the boundary point a plus beta times the value of the derivative of the function at the a is specified as some value alpha 1, and likewise some gamma times the value of the function at the other end of the boundary plus delta times the value of the derivative of the function at the other end of the boundary is specified as alpha 2, where alpha, beta, gamma, delta are constants. Now, there occurs problems in physics where there is fourth type of boundary conditions which is often used, and that is called the periodic boundary condition. So, we discuss the boundary conditions where the value of the functions were specified at the boundary points. Then there are conditions where the value of the derivative of the function is specified. One can also have boundary conditions which are mixed, where the function and its derivative take up specific values. But in physics, many times we encounter boundary conditions which are of the periodic type. The periodic boundary condition do not specify either the function or its derivative at any point, but they relate them at the endpoints. For example, we say the value of the function at one end of the boundary point A is equal to the value of the function at the other end of the boundary, the y of b, and the derivatives also at these points are equal. Now, differential equations with the specific boundary conditions are usually referred as boundary value problems. In some cases, we will see the problem can be converted into an equal integral equation. We give now the definition of homogeneous boundary value problem. If g of x in the equation shown in the 12.1 is 0, and further if the boundary conditions are of the general type, that is alpha times the value of the function at the point A of the boundary plus beta times the value of the derivative of the function at the point of the boundary x is equal to A is equal to 0, and at the other end of the boundary some gamma times the value of the function plus delta times the value of the derivative of the function is 0. Then the boundary value problem is referred to as homogeneous boundary value problem. Boundary value problems that do not satisfy all the conditions of a homogeneous boundary value problem are referred to as non-homogeneous boundary value problem. Some properties of homogeneous and non-homogeneous boundary value problems are obvious from their definitions. If Yx is a solution of a homogeneous boundary value problem, then lambda times Yx is also a solution for any constant lambda because the equation is homogeneous. More generally, if we have found the solutions y1, y2, yn, etc., then a linear combination of them, y of x is equal to lambda 1 y1 plus lambda 2 y2 plus lambda n yn, where lambdas are arbitrary constants, is also a solution. This proof is obvious. Consider the differential operator L is equal to d2 dx square plus px ddx plus q of x. This differential operator is linear. Hence, this operator acting on a y of x is equal to lambda 1, the operator acting on y1 of x plus lambda 2, the operator L acting on y2 plus lambda n, the operator L acting on yn is equal to 0. Further, corresponding to the mixed boundary condition, alpha ya plus beta dy by dx at x equal to a is equal to 0 implies sum I is equal to 1 to n of lambda I, alpha times yi at a plus beta times the derivative of yi, that is dy by dx at x is equal to a, is equal to 0, and similarly for the case other boundary point. The second property of the homogeneous boundary value problem is regarding the possibility of adding to a solution of the inhomogeneous boundary value problem. That is to say, suppose we have an inhomogeneous equation with the specified boundary conditions. Then, if we consider the corresponding homogeneous boundary value problem for the same equation, that is, remove the inhomogeneous part, then there exists the possibility of adding any solution of the corresponding homogeneous equation to the inhomogeneous part, and still this sum will be a solution of the given inhomogeneous equation. That is, let Yx be a solution of the inhomogeneous boundary value problem equation which we have considered with the general type of boundary conditions. Let Yh of x be a solution of the corresponding homogeneous boundary value problem with boundary conditions given in equation 12.7 and 12.8. Then the assertion is that the sum of the two solutions, one solution of the inhomogeneous equation and another solution of homogeneous equation, the y plus yh, also solves the inhomogeneous boundary value problem with the boundary conditions now 12.4 and 12.5. That means with the boundary conditions which are of the mixed type. The proof is again quite trivial. Now the operator L acting on the solution y plus yh. Remember, y is the solution of inhomogeneous equation, yh is solution of the corresponding homogeneous equation. So the operator L acting on y plus yh is equal to the operator L acting on y plus 0 because yh is solution of the operator and this is L operating on y is equal to gx, and alpha of ya plus yna plus beta times the derivative of yx plus yhx evaluated at x is equal to b is equal to alpha times y of a plus beta times derivative of y at x is equal to b is equal to alpha 1, and similarly we have gamma times the value of the function at the boundary b plus value of yh at boundary b plus delta times value of the derivative of the solution y plus the derivative of the solution yh at the boundary x equal to b is equal to alpha 2. We now define the adjoint forms. In boundary value problems with second order differential equations, a concept that proves to be quite useful and which is valid in many situations is the one of self-adjointness. One can regard differential equations as transformations in function space, just as finite matrices can be thought of as transformations in a finite dimensional vector space. Along the same lines, just as symmetric matrices are very useful and important type of matrices for boundary value problems, self-adjoint operators correspond analogously to symmetric matrices. To start with, we define the adjoint of an operator L. Suppose the operator L is given by L of x d2 dx square plus p of x ddx plus q of x, where p, q and L are functions which are continuous. Then the adjoint of L, denoted by L dagger, is defined as L dagger is L of x d2 dx square plus 2 dlx by dx minus px ddx plus d2l by dx square minus dp by dx plus q of x. Having defined the operator L and its adjoint, it is clear that the adjoint of the operator is the operator itself. Straightforward to see. Let us take adjoint of the operator, dagger of L dagger. Now L dagger we have defined in equation 12.7. When we take the dagger of that, we get this to be equal to Lx d2 dx square plus 2 dlx by dx minus 2 dlx by dx plus px plus d2l by dx square minus 2 d2l by dx square plus dp by dx plus d2l by dx square minus dp by dx plus q of x, and which is nothing but the operator L itself. The definition seems peculiar but would emerge naturally as follows. Let y1 and y2 be two functions that are continuous and differentiable in the domain x lying between a and b. Then let us consider this quantity L y2 into the operator L acting on y1 minus y1 the operator L dagger acting on y2. This is by using the expressions for L and L dagger is equal to y2 times Lx d2 y2 by dx square plus y2 times px dy2 by dx plus y2 qx into y2 minus y1 Lx d2 y2 by dx square minus y1 twice dlx by dx into dy2 by dx minus p of x dy2 by dx plus y1 into d2lx by dx square into y2 minus y1 dp by dx into y2 plus y1 into qx into y2. This can be written as ddx of L of x multiplied by dy2 by dx y2 minus y1 dy2 dx plus px minus dl by dx, the whole thing multiplied by y1 minus y2, which you can see is equal to dl by dx. Is equal, in fact, this is equal to dp by dx. So L dagger is called the adjoint of L, and the equation 12.19 is called the Lagrange identity. Px in 12.19 is called the conjunct of y1 and y2. Now integration of 12.19 between the limits x is equal to a to x is equal to b leads to the integral of y2 ly1 minus y1 l dagger y2 over dx from a to b. This is equal to lx into dy1 by dx y2 minus y1 into dy2 by dx evaluated between the limits a and b plus px minus dlx by dx multiplied by y1 y2 evaluated again between the limits a and b. This last equation is called the Green's identity. Now they are self-adjoint operators. Self-adjoint operators are those operators for which L is equal to L dagger. From equations 12.1 and 12.2, we get for such operators the relations that Px is equal to twice dlx by dx minus Px and Qx is equal to d2Lx by dx square minus dp by dx plus Qx. So this equation that Px is equal to twice dl by dx minus Px leads to Px is equal to dl by dx. And this equation makes the other equation that is Qx is equal to d2L by dx square minus dp by dx Qx as an identity. So using this equation that Px is equal to dl by dx, self-adjoint operators can be written as operator L, which is self-adjoint, can be written as L is equal to ddx of Lx ddx plus Qx. The Green's identity, which we obtained in equation 1220, for self-adjoint operator reduces to integral a to b dx y2x ly1 minus y1. Now L dagger is equal to L, so it's y1 ly2x is equal to simply Lx times dy2 by dx into y2x minus y1x into dy2 by dx evaluated between the limits a and b. The self-adjoint operators of the form which we have obtained, of the form 12.24, that is the self-adjoint operators which have the form of ddx of Lx ddx plus Qx, are extremely important from the point of view of applications in physics. Boundary value problems involving them, called the Sturm-Liouville problem, occur in many situations in physics, and we will discuss them in the next chapter. We now talk of Sturm-Liouville boundary value problems. In physics, the most common differential equations are of second order, as we have mentioned before, which involve self-adjoint operators. The operators are of the form that the operator can be written as ddx of Lx ddx plus Q of x, where L and Q are continuous functions. They are real and positive. The common most form of the boundary value problem involving L is of the form Ly plus lambda Vxy is equal to 0 for x lying between a and b, where Vx is real and positive, continuous and differentiable function in the domain x lying between a to b, and lambda is a number. The associated boundary conditions are of the general type. The alpha times the value of the function y at the boundary point plus alpha 2 times the value of the derivative of the function at the boundary point a is equal to 0, and beta times the value of the function at the other point on the boundary, say b, plus beta times the value of the derivative of the function at the boundary b is equal to 0, where alpha 1 square plus alpha 2 square are not equal to 0, and beta 1 square plus beta 2 square is also not equal to 0. The boundary conditions are thus of the 2-point types, with alpha 1, alpha 2, beta 1 and beta 2 as specified real numbers. Equation 12.127, namely Ly plus lambda Vxy is equal to 0, together with the equation 12.28 and 12.29 form the Sturm-Liouville problem, and the values of lambda for which the solution exists are called the eigenvalues. So what it means? What are we saying? That the equation 12.27 together with 12.28 and 12.29 form the Sturm-Liouville problem, and the values of lambda for which the solution exists are called the eigenvalues. We shall now prove some useful results for the Sturm-Liouville boundary value problems. If y1 and y2 are solutions of the equation 12.27 satisfying the boundary condition 28 and 29, then the integral over dx from a to b of y2x L time L operating on y1x minus y1x L y2x is equal to 0. Now this follows from the equation which we obtained earlier when both y1 and y2 satisfy the boundary conditions given in 12.28 and 12.29. The right hand side of the equation 12.25, which is integral a to b dx of y2 L y1 minus y1 L y2, reads for the present case L of b into dy1 by dx y2 minus y1 of b dy2 by dx at b minus L of a dy1 by dx at a y2 at b minus dy1 b dy2 by dx at a, which is equal to L at b minus beta 1 by beta 2 y1 b y2 b plus beta 1 by beta 2 y1 b y2 b minus L of a into minus alpha 1 by alpha 2 y1 a y2 a plus alpha 1 by alpha 2 y1 b y2 b. Equation 1213, that is integral a to b dx y2 x L y1 minus y1 L y2, thus follows immediately. Now we will show the orthogonality of solutions. Let y1 and y2 are the solutions of the equation 12.27 corresponding respectively to values lambda is equal to lambda 1 and lambda is equal to lambda 2 with lambda 1 not equal to lambda 2, and with both satisfying equations 12.28 and 29 respectively. Then the integral dx from a to b of y1x y2x vx is equal to 0. The proof follows from Green's identity, which is the equation 12.25, with y1 and y2 satisfying the equation 12.27. The left hand side of the equation 12.25 then reads integral a to b dx of lambda 2 minus lambda 1 vx y1x y2x. The right hand side of the equation then using 12.28 and 29 becomes L of b minus alpha 1 by alpha 2 y1 b y2 b plus alpha 1 by alpha 2 y1 b y2 b minus L of a beta 1 by beta 2 y1 a y2 a plus beta 1 by beta 2 y1 a y2a, which is equal to 0. Hence, from 12.33, equation 12.32, namely the integral a to b dx vx y1 x y2x equal to 0 follows, since lambda 1 is not equal to lambda 2. The eigenfunctions of the equation 12.27, read 12.28 and 12.29 are all real. So this result follows essentially because L is equal to L dagger and because the functions Lx, Qx and Vx are all real functions. The conjugate to the equation 12.27, that is Ly plus lambda Vxy is equal to 0, its conjugate is Ly dagger plus lambda star Vx y star is equal to 0. Y star also satisfy equation 12.28 and 29, namely alpha I y star a plus alpha 2 dy star by dx evaluated at a is equal to 0 and beta 1 y star b plus beta 2 dy star by dx evaluated at b is equal to 0. My equation 12.35 together with this boundary condition 36 and 37 shows that y star, that is complex conjugate of the solution, also that it solves the equation 12.37 with the eigenvalue lambda star. Hence, lambda minus lambda star a to b dx vx into y star x yx is equal to 0 is equal to lambda minus lambda star integral a to b dx vx yx whole square. Since vx is positive, the integral in the equation cannot vanish So yx is a square, vx is positive, therefore this integral can never vanish unless lambda is equal to lambda star, which means the eigenvalues are real. This is the, remember that in quantum mechanics you get a similar result, that if the operator is Hermitians, its eigenvalues are all real. All eigenvalues of 12.26 with 12.27 and 28 are simple. That is corresponding to any eigenvalue lambda. There is only one solution, c times y of x, with c as an arbitrary constant. We can prove it quite easily. To prove, if possible, let y1x and y2x be two solutions of 12.26 with the same lambda. Then from the boundary conditions, alpha 1 y1 at a plus alpha 2 dy 1 by dx at a is equal to 0, and beta 1 y1 at b plus beta 2 dy by dx of y2 evaluated at b is equal to 0. And since y1 and y2 are solutions, they satisfy the operator L acting on y1 plus lambda times vx y1 is equal to 0, and the operator L acting on y2x plus lambda times vx y2 is equal to 0, because both y1 and y2 are solutions. Now multiplying the first equation by y2 on the left and the second equation by y1 and subtracting, we get y2 L y1 minus y1x L y2 is equal to 0. So having obtained this, then from the structure of the operator L, which is given in equation earlier, only the derivative part of L survives in the last equation. That is y2x ddx of Lx dy to dx minus y1x ddx of Lx dy to dx is equal to 0. We can rewrite this equation as a derivative ddx of Lx into y1x dy2 by dx minus dy1 by dx into y2x. Total derivative is equal to 0. Therefore, this equation implies that this function whose derivative is 0 is a constant. That is Lx y1x dy2 by dx minus dy1 by dx y2x is some constant c. But from the equation 39 and 40, that is, we have y1 a dy1 by dx at a minus dy2 by dx at a into y2 at a is equal to y2 at b multiplied by ddx of y2 at minus dy2 by dx at b multiplied by y2 at b. Since alpha 1 square and beta 1 square plus beta 2 square and alpha 1 square plus alpha 2 squares are not equal to 0, hence the constant must be equal to 0, which means that the Wronskian W of y1 y2 defined as y1x dy2 dx minus dy1 of dx into y2 is equal to 0. Vanishing of the Wronskian implies that y1 and y2 cannot be linearly independent. Hence, y2 is a multiple of y1. This is a very important result. Existence of eigenvalues and completeness. The proof of the existence of eigenvalues of equations shown in 12.27 and their numbers involve a lengthy set of theorems which is beyond the scope of these presentations. We shall therefore state the general result, backing that up with the specific examples of equation 12.27. The theorem we state is that the Sturm-Liouville boundary value problem equation shown in 12.27 together with the conditions 12.28 and 12.29 admit of an denumerably infinite number of solutions. The eigenvalues for these solutions are all real and can be arranged in increasing order of magnitude, lambda naught, lambda 1, lambda 2, lambda m, etc., with lambda n going to infinity for n as n approaches infinity. The corresponding eigenfunctions y0, y1, y2, ym, etc. can be arranged to form an orthogonal set, which means that integral a to b vx yix yjx dx is equal to delta ij. Further, if the function f of x is such that the function and its derivative are continuous in the interval from a to b, then the function can be expanded in a series. That is, we can write f of x is equal to sum over n from 1 to infinity as Cn Fn, where Cn is given by the integral from a to b of Vx Fx ynx dx divided by the integral a to b of Vx ynx. The convergence of the series is of the uniform convergence. This equation f of x is equal to sum over n Cn Fn is known as the Eigenfunction expansion of the function. So what it means is that any function which is a solution can be expanded in terms of its eigenfunctions in a linear combination. And you should remember that in quantum mechanics, you had a situation like this, that any state vector can be represented as the sum or as a linear combination of the eigenfunctions. So, students, let us summarize what we have learned in this module. We have learned in this module that there are different boundary conditions. The boundary conditions which are called the Dirichlet type of boundary condition. They specify the value of the unknown function at the endpoints of the interval a to a and b. So, the value of the function at these two endpoints is specified as y of a is equal to ya and y of b is equal to yb. Then we have a Neumann type of boundary condition where the derivatives of the yx are specified at the endpoints, not the functions, but their derivatives or the value of their derivatives at the endpoints is specified. That is, dy by dx at x is equal to a is equal to ya prime, and dy by dx at x is equal to b is equal to y by prime. And recapitulating that, there are mixed type of boundary conditions, which is a combination of the above two types, and it specifies certain combination of the functions yx and its derivative at the endpoints. Namely, these boundary conditions look like alpha times ya plus beta times dy by dx evaluated at the boundary point x equal to a has some specific value alpha 1, and gamma times yb plus delta time the derivative of y is specified at the other boundary point b is equal to some specific value alpha 2, with alpha, beta, gamma and delta being specified constants. Then finally we have the periodic type of boundary condition which do not specify either the value of the function or its derivative at any endpoints, but relates the function or its derivative at the boundary. That is, the value of the function at the point A is equal to value of the function at the point B, for example, and the derivative, the value of the derivative of the function at the point A is equal to the value of the derivative of the function at the point B. So, given the differential equation, the complete solution involves specifying the boundary conditions. Without the boundary condition, we don't obtain a complete solution of the differential equation. Thank you.